Okay, so the next problem is just review from 141. This is already, it's a stoichiometry problem, basically. So for number 2, all we have to do is kind of read the initial problem and figure out the information that we have. So we know that the base is 0.1076 molar, and we used a total of 32.15 milliliters. Okay, so those two facts together are a great place to start. I have a concentration and a volume. I know that molarity is in liters, so I'm going to convert to liters first from milliliters. Okay, and then I know that molarity really means moles per liter, so that means I can multiply and cancel the liters. So if I do that, we can determine how many moles of KOH are used. So let's see, 0.003459. And I'm going to keep one extra digit just to make sure to avoid rounding error. I only have 4 sig figs, but I'm in the middle of the calculation, so I'm going to keep an extra one. So this is moles of KOH. Okay, so the next step is where I show how I go from the amount of KOH to the amount of acid that we have. And so that is the balanced reaction that we wrote in A. We said that it's 1 carbonic acid for every 2 KOHs. So I can create a molar ratio, where I put KOH on the bottom because I want to cancel it, and I put the acid of interest on the top. Okay, so KOH cancels, and that means that we know how many moles of acid were present in the reaction. That's the whole point of a titration, is to figure out how many moles of acid there were. Okay, and so to get concentration of the original stuff, I have to use the initial volume, the original volume of just the acid. I don't want to add any volumes together here, because that would give me the concentration of acid at the end, which is not the goal of the titration, where you're trying to figure out the concentration of the acid that we start with. So we use 25.00 milliliters. So that's our volume. We need this to be in liters, otherwise, well, you can use millimole, but it's relatively uncommon. But you can. Or you can just convert from milliliters to liters again. And so we end up going 0.003459 divided by 0.02500, and we get the final the initial concentration, 0.069187. But I only get 4 significant figures because this is a final answer. So I'm going to round. Okay, so that's question 2. We're going to need that, I'm sure, to do... Wait, I got my decimal in the wrong spot. It's supposed to be 0.06919. Okay. All right, so now the next question is, let the pH calculation begin. In our initial graph here, we said that the first calculation, A, is right there at the beginning of the chart. So that means no base has been added, 0 milliliters of base. And so this type of question is a weak acid, so I calculate the pH using our trusty ice box, right? So again, the reaction that is happening at that point is based on carbonic acid dissociation. Oh my gosh. There we go. So that was the Ka1 reaction that I wrote in question 1. Okay. And I know the concentration of H2CO3 is 0.06919 molar. I know that when this comes to equilibrium, it's going to have to use up some of that to produce H plus and HCO3. Okay, so we can use that Ka from the prior problem here, way back at the beginning. We're doing Ka1, so that'd be B here. So I'm going to put 4.3 times 10 to the negative 7 equals x squared divided by 0.06919 minus x. Now we can make the simplifying assumption here and just check it, right? We want it to be, we want to have x be less than 5% of our initial concentration. So to solve this algebra, I'm going to go 4.3 times 10 to the negative 7 times 0.06919, and that's going to equal to x squared, so I'm going to square root all of that, and so it equals x. So the answer I get from that is, let's see, so I got x equals 1.7249. Again, I'm keeping an extra figure. In reality, I actually keep all of the figures in my calculator, but I'm only writing down one extra. And I just want to check and make sure that that does not violate our 5% or so guideline. So 1.7. Sometimes this iPad makes me look like I'm a 2-year-old when I write. Sorry about that. So that 1.749 times 10 to the negative 4 divided by our initial concentration of 0.06919, and then all of that is going to get multiplied by 100%. And so I find out that this is only 0.249% of the original, so this is safe to assume that we can ignore the value of x in the denominator. So yay, no quadratic. Okay, so then the final step here is going to be to figure out what the pH is. I know x, which is H plus. So x equals H plus. So I can just say that the pH equals the negative log of x. And when I put that in the calculator, I get a pH of 3.76, which is pretty reasonable for a weak acid, so that makes sense to me. Okay, so that's 3A. So 3B is asking us to find the pH when 6.35 milliliters have been added, which we figured out is before the first midpoint. But that's going to be in the buffer area. So I just need to figure out what reaction to use, and well, we kind of already did actually in question 1. The first buffer zone is going to be the first Ka, so we're going to use this B reaction here. That's what's happening, and so all I need to figure out is the concentration of carbonic acid and hydrogen carbonate, and if I have that, I can use the Henderson-Hasselbalch equation. Again, I give that to you for the test, but the one we're going to use is going to be based on the pKa because we already looked up the pKa. And it's the log of the conjugate. That should say A minus, but I can't write a minus there because there's something in the way. But you know the idea. And while this formula does say concentration, we remember that these are in the same solution. So the volume would cancel on the top and the bottom. So I don't actually have to figure out the volume. You could. It's just an extra step you don't have to do. All right, so I know I'm going to use the Henderson-Hasselbalch equation, but in order to figure out how much A minus there is, what I need to do is figure out how much base has been used up. So that's based on the base is based on the volume, and again we're gonna use dimensional analysis to show the work properly, and it's based on the concentration because volume times concentration gives us moles. So I know that I don't even have to put an equal sign there. I know the molar ratio of carbonic acid is 1 carbonic for every 2 NaOH, so I can convert right there. And so we figure out that there are 3.46 times 10 to the negative 4 moles of, oh, sorry, actually, let me just back up here. Well, no, this is all right. We can use this. It would have reacted with this many moles of carbonic acid. I also know from the last problem how many moles of stuff were there to begin with. Not the last problem, the one before that. I know that we have this many moles of carbonic acid total. So if that's true, I can take that number. So we started with 0.0017297, and we're subtracting the 3.46 moles. These are all moles. I can't subtract molarity, so don't be confused by that, because that would imply the volume is changing, and if you subtract when the volume is changing, things get funky. But you can subtract moles and moles, so that's what I do. That tells me that 1.388 times 10 to the negative 3 carbonic acid is left. Okay, so that is HA in this equation. It's H2A technically, but you know. And I know how many moles of HCO3 formed because I know how many moles of, H2CO3 reacted. So, you produce 1 hydrogen carbonate for every H2CO3 that reacts. You could properly show this using a mole ratio again, or you could have done it here as HCO3. Either way works fine. Okay, but you get the same numeric value. So all we have to do now, the final step for this one, is to plug it into our equation. pH equals pKa, so that'd be the negative log of the Ka. And this reaction, we decided, is the first Ka, so I'm going to choose to put in 4.3 times 10 to the negative 7 plus the log of HCO3, so that's 3.46 times 10 raised to the negative 4 divided by the amount of H2A or H2CO3 that's left, which is that. Okay, so what we end up with is that the pH equals 6.366 is what the calculator says for the pKa, plus the other logarithm there is negative 0.6089, so I take those two together and I get a pH of 5.76.